Welcome back to the deep dive.
So when you hear the word network, I think most of us, we immediately picture the internet, right? This huge invisible thing that spans the whole globe. But when you actually start to, pull on the technical threads, the sheer variety in network sizes is just, well, it's staggering.
It really is. I mean, we talk about networks with millions of devices that cross entire continents, but then you also have networks that are like just two devices.
Two devices.
Yeah, two devices sitting maybe 10 feet apart. And what's really key here, the important thing for you to get your head around, isn't just that these different sizes exist, it's understanding the 5 main ways we classify them.
And that classification, it all comes down to physical size, to geography and scope.
Exactly. It's all about geography.
Okay, so let's unpack this. Our mission for this deep dive is to cut through all that noise and give you a really solid framework for understanding these classifications. We're going to start with the smallest possible connection, like think your phone and your watch, and scale all the way up to the massive cables that are literally buried under the ocean.
Let's do it. So we start at the absolute smallest scale, basically what's in your pocket.
Right. We begin with the personal area network. You'll see it called a PAN.
PAN.
And this is the definition of local, ultra-local. We're talking about networks that cover very, very short distances, usually up to a maximum of about 10 meters or 30-something feet.
And just a handful of devices, I assume.
A minimal number, yeah. Often it's just 2.
The source material gave the perfect example, your mobile phone and a wireless headset connected with Bluetooth. But it's more than just audio, isn't it?
Oh, yeah. Think bigger. It's all of your personal peripherals, your smartwatch, your fitness tracker, even your wireless keyboard and mouse talking to your computer.
So it's a network that's really built around one person's convenience.
Exactly. The key thing with a PAN isn't just how close the devices are, it's the technology. They rely on low power, low speed stuff.
Like Bluetooth.
Like Bluetooth, or sometimes you'll see Zigbee. They're built for efficiency, not for speed. It's why they're perfect for, sending a quick status update from your watch or controlling your music. But you wouldn't try to download a 4K movie over your PAN.
Right, that would be painful. That distinction, low power, minimal data, it really defines the PAN.
Okay, so from there, we take a step up to the network that pretty much every home and office has. And this is where the definitions, I think, get a little more complex. The local area network?
The LAN.
Yes.
Or LAN.
And the LAN is an immediate and pretty significant jump in scope. It covers a much larger area than a PAN, and crucially, it's built to handle dozens, maybe even hundreds of connected devices.
These are your classic home or office Wi-Fi networks.
Exactly. They're defined by higher capacity technology. We're almost always talking about Ethernet cables and, robust Wi-Fi standards.
So the LAN, we're moving from devices just talking to you to devices talking to each other across a whole building, or maybe one floor of an office. But the source material brought up a really interesting gray area, and it kind of challenged what I thought I knew. If a LAN is about capacity, what happens if I just connect 2 computers with an Ethernet cable? Is that not basically a PAN?
That's a fantastic point, and that's where the nuance is. It's not about how many devices are using it right now. It's about what the network could handle. The architecture itself dictates the classification.
I see.
So if you connect 2 devices using hardware, say an Ethernet switch and some proper cabling that is designed to support 50 devices over 100 feet, you're dealing with LAN infrastructure, period.
So it's about the potential. It's about the hardware standards underneath. A PAN uses simple, short-range protocols. A LAN uses faster Ethernet protocols and dedicated hardware like switches and routers, even if it's not being fully used.
Precisely. And another thing that sets a LAN apart is administration. In an office, for instance, the whole LAN is usually governed by one IT department.
Right, so they control everything, security policies, IP addresses, all of that.
All of it. That single administrative boundary is key. We've officially moved from the desk to the entire building.
That makes perfect sense. So administrative control and dedicated higher speed hardware. That's the LAN. Okay, let's scale up again. We're heading into the mid-range now. Networks bigger than a building, but not quite a whole continent yet.
Right. And that brings us to the next level up. The campus area network, or CAN.
CAN. This is one I think a lot of people get mixed up because it sits in this weird middle ground geographically. It's bigger than a LAN, but it's smaller than the citywide network we're about to talk about. So what actually defines a CAN?
The single defining feature of a CAN is that it's designed to connect several different LANs together.
Okay, so a network of networks.
In a way, yes. Think of a big university campus or maybe a large company with multiple buildings on one property. Each building probably has its own separate LAN, its own little subnet. But all of those individual LANs are connected and managed centrally.
For one IT department.
By one IT department,
Yeah.
exactly.
So it's less about the total physical distance and more about that hierarchical structure.
Yeah.
You'd need some pretty serious hardware, I imagine, like powerful routers, to manage all the traffic between these separate networks.
Absolutely. The technical complexity really jumps here because you're dealing with what's called intra-campus routing, managing Wi-Fi across 5 huge lecture halls, for example, making sure students can walk between them without dropping the connection.
That sounds like a nightmare.
It requires very specialized hardware, and it's all overseen by that single central authority. The CAN structure lets an administrator treat 5 separate city blocks as one single unified network.
That centralized policy is the key takeaway then. You can have the same rules, the same security in building A and building D because the CAN makes sure the traffic between them is optimized under one big organizational umbrella. Okay, now we're ready. Let's take the biggest leap in this mid-range. We're leaving the campus and going to the city limits.
We transition now to the Metropolitan Area Network, the MM.
A man. And this one is defined pretty explicitly by its size, right? It's a city-sized network.
A city-sized computer network, or sometimes just a large part of a city. That's the definition.
We're talking miles here, maybe tens of miles, and a serious amount of data. So if a man is connecting a bunch of different LANs all over a big urban area, what kind of technology do you need to handle that scale?
Well, the shift is pretty fundamental. The sheer scale dictates the infrastructure. To move that much data reliably across a whole city, AMANs are almost always connected using fiber optic cabling.
So we're way beyond standard copper Ethernet cables at this point.
Oh, way beyond. We're talking about high-capacity, dedicated network backbones. Sometimes you'll hear the term dark fiber.
Dark fiber. That's the fiber optic cable that's already in the ground but isn't being used yet, right? It's just waiting to be leased and lit up.
Exactly. And that infrastructure is what enables that super high-speed, low-latency communication across the city. The reliance on fiber also means that MANs often have different owners than a LAN. A MAN might be owned by a big telecom company that sells access to local businesses, or even by the city government itself.
That's a really crucial detail, because the management challenges must just explode. On your own LAN, you control everything. On a MAN, you're relying on a backbone that you might not even own.
And you have to account for latency, for the delay caused by pure distance, even with a fast connection.
So we've gone from the desk to the building to the campus, and now we've covered the whole metropolitan area.
Precisely. We've pretty much exhausted the personal, local, and mid-range scales. Now it's time to jump into the stratosphere.
The 5th and largest category. This is where the idea of a geographical limit almost starts to break down.
This is the wide area network, the WAN.
The WAN, the ultimate umbrella network.
The WAN is the computer network with the largest possible geographical area you can imagine. It's designed to span huge distances, regions, countries, as you said earlier, entire continents. Its defining characteristic is its sheer scale and its hierarchy.
And the WAN is so big that it actually contains all the other network types we've just talked about.
Yes. Your home LAN connects to a MAN, which connects through a huge provider's infrastructure. And all of those are just small pieces inside the much larger global WAN.
And if we need one single perfect example of a WAN, it's the internet.
It's the internet. The network that's letting you listen to this deep dive right now, the internet is the quintessential wide area network. It's the thing that links all of these hundreds of thousands of separate private and public networks together.
The technical challenge of that is just mind-boggling. I mean, we talked about simple routing inside a LAN. How in the world does a WAN manage routing traffic between continents and all these thousands of independent networks?
It's managed by very specialized, very advanced routing protocols. For example, routing traffic inside your campus, inside the CN, is handled by one set of rules. But connecting your network to another major network on the other side of the planet,
That's a whole different ballgame.
it requires a different protocol, something like BGP, the Border Gateway Protocol. This lets all the big routers talk to each other and figure out the best path across all these independent networks, optimizing for, distance, cost, everything.
So BGP is kind of like the global postal service for the internet, figuring out the most efficient route for your data packets to travel between New York and Tokyo.
That's a great way to put it. And the source material highlights that this whole system isn't magic. It depends on some monumental physical infrastructure.
Right.
Absolutely. The source actually pointed to a really cool resource for this. If you really want to see the physical reality of the WAN, you should look up the submarine cable map. It's at submarinecablemap.com.
Oh, I've seen that. It's incredible. When you see those thick fiber optic lines, thousands of miles long, just running along the ocean floor connecting North America to Asia or Europe to Africa,
Yeah.
that's when the concept of the WAN really hits you. It's a real physical web.
And that physical map also shows you the real-world challenges. These cables are often owned by groups of telecom companies. The only reason the global WAN is reliable is because of redundancy. If one cable gets cut by a ship's anchor,
Which happens.
it happens. But there are usually several other paths the data can take to make sure your connection stays up.
It's such a powerful illustration of how network classification isn't just some abstract idea from a textbook. It dictates everything. Governance, technology, and just massive, massive infrastructure investment.
The physical geography dictates it all, from the tiny low-power chip in your headset to the dedicated fiber lines crossing the Atlantic Ocean.
So let's bring this all together for everyone listening. We've covered the full spectrum, classifying networks by size.
We started with the smallest, the PAN, the Personal Area Network, confined to about 10 meters, defined by low-power convenience tech like Bluetooth.
Then we expanded to the LAN, the Local Area Network. This covers a building or a home, and it's defined by its high-capacity infrastructure and single-owner administration, usually using Ethernet.
And those LANs can then be grouped together into a CAN, the Campus Area Network, a collection of interconnected LANs all under one central administrative structure.
From there, we scaled up massively to the city-sized MAN, the Metropolitan Area Network, which relies on those dedicated, long-distance fiber optic backbones to link everything together across a huge region.
And finally, encompassing all of them, the continental scale WAN, the Wide Area Network, defined perfectly by the Internet, which uses sophisticated protocols like BGP to route traffic across the entire globe.
The key takeaway is really pretty simple when you break it down. Network classification is all about geographical size, and that size then determines the technology, the hardware, and the authority needed to run it.
Right. And while we've really focused on the size and the geography of the network today, the source material pointed out that the next logical step in understanding all this isn't about the physical boundary anymore. It's about the internal layout.
That's a great point. It raises a really interesting question for you to think about. If classification defines the boundaries of a network, how do we define the shape inside those boundaries? We've looked at the scale, but not the structure, not how the devices are actually arranged, physically or logically, inside the LAN or CAN.
Exactly. So we'd encourage you to start thinking about how networks aren't just defined by how big they are, but by their structural blueprint. That next step, defining those connection patterns, is a whole field known as network topologies. Something to chew on as you continue to navigate this vast, interconnected world of the wide area network.